Of my colleagues, Ron Vassar, Paul Benson, Alex Landy, and Dave Resnick. And I want to begin with this graph. This is the opportunity for selection, standardized variance in fitness from the guppy population in Trinidad, graphed against density on the lower axis, on the horizontal axis, and you see that it goes up. Why does it go up? That's the question. So in this talk, I'm going to first tell you answer this question. Why is this question interesting? Why should you care? Secondly, I study it with guppies. And third, which patterns emerge. The short answer to the first question is that there are four hypotheses for why that pattern might arise, each of which would take us down a different subsequent path of research to understand how fitness is actually structured. And so that's why the question is interesting. And let me go over those four hypotheses briefly, and I'll use a couple of cartoons to help illustrate this. The first one is very simple. Imagine a selection gradient that looks something like this. And in this hypothesis, we have nothing but a case of phenotypic plasticity in the trait, that increasing density changes the distribution of the trait. So for example, this is what the trait distribution might look like at low density. The vertical lines kind of represent, with the two-headed arrows, represent the variance. And I want you to see, the mean might be in the middle, but I want you to see that because the trait value distribution corresponds to where the graph of relative fitness is shallow, that this produces a relatively low variance in relative fitness and a high mean. At high density, the trait value might be lower, the variance might be higher, and therefore you get a much larger opportunity for selection. So it's very simple, and here the follow-up question would be, not just why the trait value decreases with density, but why does the spread among individuals increase? So that would be an interesting question. The second one is more a question about the ecology of selection. Here you might have a situation in which the gradient at high density is steeper than the gradient at low density. And we can make the gradient go in the opposite direction. It doesn't matter. It's merely a matter of the steepness of the gradient. And here, even the same trait distribution at low and high density will give you that result. Here's the low density distribution again. Here's the high density distribution, meant to depict the same distribution. Lines are offset for clarity. And I want you to see that even in this case, you will get the result of relative fitness being more variable at high density than low density. Third hypothesis is really one about the complexity with which selection acts. So for example, at low density, you may have a situation where the bulk of selection is focused on one trait, but at high density, other traits are recruited to determine fitness through the ecology of what happens at high density compared to low density. And depending on the covariance among the traits, this could also produce a higher relative variance in fitness. And the fourth hypothesis is what I call the Morton-Salt hypothesis. When it rains, it pours. When you're already in a situation in which your absolute fitness is low, for example, high density, small deviations in the environment can make a big difference. So for example, the analogy being, if you're standing at the edge of the cliff, which is a precarious position, a shove 1 or 2 inches to the wrong direction and you're over the cliff. If you're 6 feet back from the cliff, a shove of 1 or 2 inches doesn't do you much harm. So here the argument for the subsequent research is that why in the most stressful of environments, every little thing makes it worse. When it rains, it pours. Or as a famous Rosanna Dana once said, if it's not one thing, it's another. But we'll go with the Morton-Salt hypothesis. Now, this is the pattern we want to explain. Why would we study it with these organisms, guppies? Well, the real reason is that we have some populations of guppies that are ideally suited for this situation. As part of a larger project, we transplanted guppies from a high predation stock downstream on your lower left, across many barrier waterfalls into an area upstream that had no guppies, but with killifish. And we did this in a controlled experimental design with 4 different streams. So now we have 4 populations that we have followed in monthly censuses over 10 years. But what really makes this work, there are two things that make this work, and this is the first one. Every guppy is marked individually. We have a capture probability of about 90%. And so this means that every month we can tell you where that guppy, we know where the guppy was, we know who it was, and we can photograph it every month and know some of its trait distributions. We start when they are first recruited into the adult population, and we continue until they leave the population, usually through death. And I'm going to talk about one of these populations, the one labeled lower lava on the upper right. And the reason is we have additional information for this. We have every individual genotype with 43 microsatellite loci, which means we have a probability of assigning parentage for one parent, the mother, for about 85 to 90% certainty. Two parents, it's less, but one parent is very high certainty. So we know the distribution of reproductive success. Reproductive success, or fitness, is defined as when the progeny is recruited to the adult population. So we actually know this. So for example, this female here, she had 16 offspring from 1, 2, 3, 4, 5 different males. So we know fitness very, very well. So what I'm going to do is explore the structure of fitness. On the far left-hand side, this is the graph of biomass density at lower lava for the first 100 months of the study. I've waited all my life to say that, the first 100 months of the study. But that's not important. What's important is the lower left is the lower density, and I'm going to talk about the structure of fitness up in this region here where the density is much higher. So I'm going to break it into two discrete blocks. And I'm going to explore the relationships among fitness, defined as the number of each female's progeny recruited into the adult population, size of maturity, the standard length of each female when she was recruited into the adult population, lifespan, the number of months each female was captured. That's not really a trait, it's kind of an epiphenomenon, but it's very important, a very important correlate of reproductive success. Riffle use, the proportion of each female's life spent in riffles versus pools, the other habitat. This is an ecological attribute, but one that is important. And something that I call experience density, the average density each female experiences in her lifetime, to be illustrated. And look at these relationships, not just between fitness and the other predictors, but among the predictors themselves, which change between low and high density, at lower overall or higher overall density. So first I show you the graph of the number of recruits. You can see that overall density across the whole study, the recruits go down with density. This is the histogram on the left and the right. I want you to see that, and I'll show you a number of graphs like this, the coefficient of variation, the square root of the opportunity for selection, is higher at high density than low density. And if you're good at multiplying your decimals, you'll know that the opportunity for selection is about 20% higher here than here. So the data I'm bringing to bear on the question is in fact suitable for the question. I'm going to show you a series of graphs like this. This is the exploratory data analysis phase. There'll be scatter plots in which the lines on the scatter plots are low S curves, the non-parametric smoother, so I do not assume any particular form, and the histogram will be at the bottom. So this is the histogram on the bottom of length and maturity and the relationship of length and maturity to the number of recruits. And you can see that it looks like there's some kind of effect, roughly starting at about 16 millimeters. There's a leap up in the low density, a turn up in the high density, perhaps. But what I really want you to see is the histogram at the bottom, which is that the relative variance in length and maturity at high density is not greater than the relative variance at low density, meaning hypothesis 1 is not consistent with the data. Or, if you write it the other way, the data are not consistent with hypothesis 1. Either way, this is a problem. This is lifespan. I want you to see in the scatter plot that on low density, number of recruits seems to increase gradually with lifespan. And yes, I know how noisy the data are. These are real data from the field. On the right-hand side, the low S curve seems to turn up abruptly, just about at 20 millimeters. But what I really want to call your attention to at the bottom is that the relative variance in lifespan at high density is no greater than the relative variance at low density. Another smack in the face for hypothesis 1. This is the average riffle use over time. As time goes on and density increases, females spend more of their time in riffles versus pools. Why do we care? Well, for one, there seems to be, in the low S curves, a rise in the number of recruits with more time spent in riffles. Come back to this. I want you to see in the histogram, though, that again, there's not more relative variance of high density than low density. Another slap in the face for hypothesis 1. This could be hypothesis 2, if that's really steeper. Certainly the lifespan was, but we shall see. Now, It's important to understand the relationships among the predictors, the putative predictors of fitness, and here I show them to you. Lifespan at the top against length of maturity, on the left at low density, the left at high density. You be the judge of whether those low S curves tell you anything. On the bottom, you have riffle use as a function of length and maturity, and I do want you to see that depending on how much you love low S, there's either a modest decrease in riffle use with increasing length and maturity or no relationship, whereas this suggests that there might be an increase in riffle use at higher lengths of maturity past about 16 or 17 millimeters. Now this is interesting because as it turns out, there are not a lot of fish in riffles compared to being in pools. Riffles, and our intuition as naturalists have always been that riffles are a miserable place to live. And if you let the fish to tell you the answer, this suggests that that's true. This is the density in pools and riffles for our four populations. And lower Lavaha's the second. And what I want you to see, and they're all on the same scale, is that the density is much, much higher by several fold in pools than it is in riffles. Which means the more time you spend in riffles, the lower density you're going to experience. Yes? I'll prove it. What we want to do is look for each individual fish, what density did it experience? We usually measure overall density, but in fact, every individual doesn't encounter the same density. This is where we come into what I call experience densities. The average density an individual experiences over its lifetime as it occupies either pools or riffles. It's just the sum of the density in the habitat where individual J was found in month I divided by the lifespan. And this is where that 90% capture probability comes in really, really handy, because we know where they were every single month. So for example, if we have an individual who was in a pool in January of 2009, the density of the pool was 3.2 grams per square meter, was in a riffle in February at a much lower density. On average, this individual experienced 2 grams per square meter. What happens is that as riffle use increases, experience density drops very fast at high density. And why that's important, the number of recruits increases as the experience density goes down. That's these lines at the bottom. Okay, enough of the folderol. Enough of the exploratory data. Get to the hardcore statistics. Actually analyze the number of recruits with a negative binomial error structure in the regressions. This is the best fitting model. And in fact, the best model, I'll show you the two best models in low and high density, as determined by the ratio of the residual deviance to the residual degrees of freedom, which is what you have to do with negative binomial error structure. I want you to see that low density is a very simple situation. The later phase, high density, notice that the regression coefficient on length and maturity is the same. These are all significant. I rounded them to 2 decimal places just to help your appreciation for them. Lifespan is a much steeper relationship and positive, but notice how big the relationship is with experience density, and it is negative. This would suggest the Morton-Salt hypothesis is actually accurate. But if you remember that at high density, there's an increased chance of riffle use with increased length and maturity, that means that the density effect also includes a force of indirect selection favoring larger size and maturity. So what's happening is that you have the same direct relationship but indirect selection. Conclusions. The higher levels of relative variance are driven by a more complicated architecture of fitness. Direct selection coefficients can be, but not uniformly are, larger at higher densities. So that's hypothesis 2, and that's particularly so for lifespan. Size and maturity has no relation to habitat use at lower densities, but at higher densities, the individuals that were larger at maturity use lower density habitat. And that's the gong, and experience density suggests the Morton-Salt effect. Thank you very much for your attention. Sorry for that.